You did these in Algebra 2, so this is not completely new. Really, the new pieces, we may add some uglier functions in here, and then we will talk more about the domain than you did, or domains and ranges, but really, otherwise, it's all stuff that you've seen before. So remember, you know that if something is a function, that means x never repeats. If it's one-to-one, that's saying y doesn't repeat. Okay, it's basically saying every x you put in gives me a different y value. I can't put in two x's that both give me the same y back out. So everything has to be unique. So first we're just going to look at an example and tell me if this is one-to-one or not. So you're shaking your heads no, because the 38 gets repeated. My abbreviation for one-to-one, I do 1-1. So that's not one-to-one because of that 38. What about the second one, the set of ordered pairs? Yes, if I look, all of these y's are different numbers, so that one is one-to-one. Okay, so if we have a set of ordered pairs or a mapping, it's pretty easy to look at and see. If I give you the equation, it's a little bit different. So I'm going to show you two ways of doing it. First way is the algebraic way. Just like, remember when we were trying to decide if things were functions or not, we talked about how to figure it out by looking at the equation, and then we talked about how to figure it out from the graph. So that's what we're going to do here. If it's one-to-one, y can't get repeated. So if you have a graph that is one-to-one, can I put in two different x's that have the same height on that graph? No, that's the definition of one-to-one. That would not work. So what we will do is actually start out assuming you have the same y value twice. F of A equals F of B. So we'll start out with that assumption, and we will work it out. At the end, if it's one-to-one, then we will get A equals B. In other words, saying the only way you could have got the same y twice is if you plugged in the same x to begin with. But if we solve that and we get anything else, like A equals B plus 1, or A equals plus or minus B, then it is not one-to-one. So for instance, we're going to show this on a couple, and then I'm going to give you another alternative if you don't like the algebraic way. So if I want to decide if this is one-to-one, we're basically going to start out pretending it's not. So we're going to pretend we hit the same y value twice. So we're going to say F of A equals F of B. So F of A, if you plug an A into this, you get negative 3A plus 7. F of B, if you plug a B into this, you get negative 3B plus 7. Now I'm just going to solve for A. So if I want to get A by itself, we can subtract over the 7. We have negative 3A equals negative 3B. Divide by negative 3. And we get A equals B. So what we just saw is the only way we hit the same y value twice is if A and B are the same number. So if you work it out and you get A equals B, that means it is one-to-one. So another one. If I want to start out assuming we get the same y value, F of A equals F of B. So if you plug an A in, you get the square root of 49 minus A squared. If you plug a B in, you get the square root of 49 minus B squared. If you want to solve for A, what would you do? Square. So the square root and the square cancel. And then we subtract our 49. Then what would we do? Divide by squared equals b squared. Then what do you do?
Square.
If you add a square root, what else do you need? Okay. So what this tells me is I could put in two different numbers and get the same y value. For instance, if I put in positive 7, I get square root of 0, which is 0. But that's the same as when I put in negative 7, I get square root of 0, which is 0. So both positive 7 and negative 7 gave me the same y value, so is this 1-to-1? No. Now, the nice thing about these, we're talking about functions all the time. And if we have a function, it's really easy to get the graph from our graphing calculator. Can you tell me, just by looking at this, do you know what would be something to look for in the equation that would make it not 1-to-1? Like b turned out to not be 1-to-1. What did it have in there that you think created that problem? The square. So you need to watch for things like squares, even powers in general. X squared, x to the 4th, x to the 6th, that's going to be an issue. Absolute values would create an issue. But we can also think about this in terms of a graph. We know if it's a function, it passes the vertical line test. If x never repeats, no matter where you draw that vertical line, it only hits it once. So if it's 1-to-1, y doesn't repeat, so that means we could use the horizontal line test to decide. So if it is 1-to-1, it has to pass the horizontal line test. That means if you had your graph, no matter where you drew a horizontal line, it can only hit it once. So this one would be 1-to-1. But in contrast, like an x squared, it's a pretty pathetic one, but we could see there are lots of places you could draw that horizontal line that would hit that graph twice. So that is not 1-to-1. So very easy to determine whether or not it's 1-to-1 just by looking at the graph. And we do have our calculators available, so that's something that we could quickly look at. So I want you guys, I'm going to change this because I just used this example. Let's say this is the absolute value of x plus 1. I want you to decide if each of these are 1-to-1 or not. So draw yourself a quick little graph, use your calculator if you need to, and decide if it's 1-to-1. Look like?
V.
So v, that plus 1, if you add to the x, remember it moves it to the left. So it looks roughly like this. So is that 1-to-1? No. B, x cubed, that's just your chair. So is that one 1-to-1? Can everyone tell from the graph if it's 1-to-1 or not? You know what we're looking for? One thing about these, if you have a function that's either always increasing or always decreasing, it will be 1-to-1. You know, that x cubed, it's going up the entire time. It's always increasing, it's 1-to-1. Think about a cube root. You know, it's always increasing. If you have a function that's always decreasing. Basically the issue we get an issue when you are decreasing and you switch to increasing. It's when you change directions that you get those things that don't pass the horizontal line test. So a lot of those polynomials that we were graphing on our test yesterday, you know, we were going back and forth, we had those curves that were going back and forth hitting the different intercepts. Those didn't pass the horizontal line test because you were switching back and forth between increasing and decreasing when you graph them. All right, so why do we care about, or why do we care if it's 1-to-1 or not? If something is 1-to-1, then it has what we call an inverse. An inverse is like the opposite of something, the exact opposite. So we find it by switching x and y. So essentially your x and y are just changing roles. The notation, f to the -1, just make sure you're familiar with that. That doesn't mean 1 over something like we normally think of with a negative power. That is just the symbol for an inverse. So we're going to start out finding inverses of just a very basic set of order pairs and make sure we can find the inverse for each of those. If I give you a set of points, all the inverse does is flip the x and y. So if your point is -3, -27, then the point in the inverse would be -27, -3. We are not changing the signs, we're just changing the order. So -2, -8 was in the original, so the inverse would be -1, -1 was in the original. So in the inverse, if you flip the order, they're the same number, so that didn't change. So we still have 0, 0, we still have 1, 1. We had 2, 8, so that would become, and then we had 3, 27, so that would be, so you guys do B. Find the inverse for that. So what are they?
5,
Okay. So far, so good? So if you notice, the domain of the original, those are the x's. In the inverse, that domain turned into what? The y, so it became the range. So the domain of the function will always be equal to the range of the inverse. The range of your original function, that's the y's in the original, they become your x's, so that's the domain of the inverse. So on a lot of these problems, when we start finding inverses, I'm going to say, give me the domain and range of both. You're not finding 4 different things. If you've got the domain of the first one, you automatically know the range of the second, and vice versa. So it's not a lot of work to find that. One other thing, since I told you that a function and an inverse are opposites, that means they cancel each other out. So, for instance, if I said I'm going to add 2 to a number, what's the opposite of that? Subtracting 2. So if I start with a number, let's say I'm going to start with 7. If I add 2 and then I subtract 2, what do I get back? 7. Okay, what if I flip the order? What if I start with my 7 and I subtract 2 and then I add 2? 7. Because they're opposites, if you do both operations, they will always cancel each other out and give you what you started with. So when you compose them, the inverse composed with the original or the original composed with the inverse, if they are inverses, you will have to get x back both times. So there's going to be some what we look at and we're trying to decide if 2 functions are inverses, and we can compose them. If we get x back for our answer, then yes, they are. They cancel each other out. If we get something different, then they are not. So let's do that. Let's decide if these things are inverses. So we would have to find G composed with F, and we will need F composed with G. It's not enough to check both, or check one, you have to check both every time. So G composed with F. Remember, when you do compositions, you start on the inside. And I'm going to take that and plug it into G. So G is whatever you put in cubed. So that would be the cube root of x cubed. And what does that give us? X. So far so good. We can't stop there. It is possible for one of them to equal x and the other one not. So we do have to check the other way. So if I did F composed with G, so that's F of x cubed. So if I plug x cubed in here, I get the cube root of x cubed, which is x. So those are both x. That means these are inverses. Let's do it. I want to see if these are inverses. If they're inverses, that means they cancel each other out. So we will do F composed with G and G composed with F, and both of those things have to equal X. So F composed with G. That means I'm going to go to F, and I will replace my X with 1 over X minus 1. When we do this, if I'm working with the denominator, you can combine like terms, so you get 1 over X minus 2. Is that the same thing as X? Let's see, is there anything we could do? We don't like fraction within a fraction, so we could take top and bottom times X. If I did that, I would get X over 1 over X times X is 1 minus 2 times X. That's still not X, and there's no way I'm going to get this to just equal X. So there's no need of checking the other direction. What do I already know? They're not inverses. If one of them doesn't turn out to be X, you can stop and just say these things aren't going to be inverses. So I would like for you guys to do the next one. Check if these are inverses. So F composed with G. Okay, when you plug this in, you're replacing your X with this 1/3 times X minus 4. If you distribute 3 times 1/3, it's just a 1. So then you get X minus 4 plus 4, which is X. So that way it worked. Can I stop?
No.
No. Check the other way. Oops. So G of the 3x plus 4. So that's 1/3 times, and I have to do my 3x plus 4 minus 4. So positive 4 and negative 4 cancel. You're left with 1/3 times 3x, which is x. So these are inverses. Are you okay with that? In terms of a graph, because x and y just flip roles in the inverse, the graph itself, if you graph the function in the inverse, it's always going to be symmetric across the line y equals x. So I want to illustrate that just with an example to kind of show you what I mean. If I asked you to graph the inverse of y equals 3x minus 2. So let's first graph this line. So that's a line, y-intercept is -2, slope is 3, so you go up 3 and over 1. So there's my original line. Without knowing anything else, how would I graph the inverse from this?
Just do the opposite.
Yeah, we have 2 points, don't we? So this point is 0, -2, so what point would be on my inverse? -2, 0. This is the point 1, 1, so what point would be on my inverse? Still 1, 1. So there's my inverse. I said those things are symmetric across the line y equals x. Y equals x is a line, y-intercept of 0, slope of 1. So do you guys kind of see that if you folded on that red line, the blue and the black would overlap each other? So that's just a quick check you can do for yourself to kind of see if you've done your work correctly. Just think about that line y equals x. If I fold on that line, the function and the inverse should overlap. That's the line of symmetry for them. Any questions there? So there's some on your homework, kind of like this, where I just give you a graph and ask you to graph the inverse. So all you have to do is find the points, and we should be able to get the inverse from that. So for instance, this point, I don't think my graph is totally square here, but it's close. This is point -2, -2, so that would still be the point on my inverse. This is -1, 0, so on my inverse it would be, so there's that first little line. Okay, I've got 0, 1, so that would go to, I've got 1, 2, so that would go to, think about if you drew the line y equals x, it should go right through the middle of this. So it's symmetric across that. Just a quick check for myself to make sure my graph matches up. All right. I'm flying through here. Everybody's good with everything so far? So I want to wrap this up with actually finding inverses. And finding inverses, there's certain steps that we have to do. First of all, if it's written in function notation, you have to change your f of x to a y. Then we know an inverse switches x and y, so that's what we're going to do. Every x will turn into a y. Your y turns into an x. Then we will solve for y, and then we'll put it back in function notation. Change that y to f inverse of x. So let's look at what I mean. Here's an example. Step 1 is change f of x to a y. Step 2. What does an inverse do? So if I do that, I get x equals 2y plus 3. Now, if I want this written in function notation, I have to have it y equals. So to get the y by itself, we would subtract over the 3. Divide by 2. Final step, instead of y, what do I put? The f to the negative 1 of x means f inverse of x. So there is my inverse. Let's do another one. Okay. So if I want to find my inverse, first step, then we switch x and y. Because I have multiple x's, that means now I'm going to have multiple y's. Now we have to solve for y. So first, if I want to get rid of the fraction, we can multiply by y minus 1. So if I distribute, that gives me xy minus x equals 2y plus 1. I have more than one y here, so what should we do? You guys just ready to give up? Nobody has any idea what I might do now? Okay. Okay. Let's get all the y's on one side and everything without the y on the other, and then we'll get to that point. So if I want to bring my y's over, I need to subtract over this 2y. I'm going to add my x. Now xy and 2y, they're not like terms, so they just both stay. But now both of those have a y. So I can't actually subtract them, but I could factor out that y. And so then, to get y by itself, you would divide. So final step, instead of y, we write f inverse of x. So f inverse of x is 1 plus x over x minus 2. This one they also asked for domain and range, and I want the domain and range of everything. I want the domain of the function, the range of my function, the domain of the inverse, and the range of the inverse. So let's start with the function. It's a fraction. We know that in a fraction the bottom can't be 0. So what can x not be? Positive 1. So the domain of my function is negative infinity to 1, union 1 to infinity. And the domain of the function is equal to what other thing? Now, as far as looking at an equation and finding the range, that's difficult. But let's go to the inverse. Could you tell me the domain of this inverse? It can't be positive 2, so the domain of the inverse is negative infinity to 2, union 2 to infinity. And the domain of the inverse is always equal to the range of the original function. So when I ask for the domain and range of all this stuff, all you really need to do is the domain of the original and the domain of the inverse. And that will give you the missing ranges. We're going to do at least one more, but I am going to change the next problem. I want to do another fraction. I think we probably need another one like this. So let's scratch this problem. And let's make this x minus 5 over 2x plus 3. So first step, change your f of x to a y. And then, what do we need to do? Switch the x and y, yeah. So now we can solve for y. We want to get rid of the fraction, so we multiply by the 2y plus 3. Let's cancel. We distribute your x, we get 2xy plus 3x equals y minus 5. We're trying to solve for y, and we have more than one y, so what do I need to do? Y is on the same side. Doesn't matter which side I bring them to. Nope, not at all. So I'm going to add over my 5 and subtract my 2xy. And we get 3x plus 5 equals y minus 2xy. So then, you can pull out a y, which leaves you with 1 minus 2x, and you divide.
How did you get rid of the y on the next one?
I factored it out. So it's out in front. If you distribute it, you get back to what you started with. Just like if I gave you x squared minus 3x, you would factor out that x and it would leave you with an x minus 3. I just took out the y there. Final step, instead of y, we need f inverse. So I have 3x plus 5 over 1 minus 2x. If you did this and you had moved everything to the other side, you might have negative 3x minus 5 over 2x minus 1. That's equivalent. Both answers are the same. So either one is fine. So if I want domain and range, I know the domain of the function is equal to what other thing? The range of the inverse. So if I look at my original, what can't I have? And the range of the function is equal to the domain of the inverse. So if we go to our inverse, what can x not be there? So this one, I'm talking about x squared. And in general, functions have to be one-to-one to have an inverse, because otherwise, if they're not one-to-one, when you flip x and y, it won't be a function. This one is not one-to-one. So the only way I'm going to be able to find an inverse is if I'm only looking at part of it, which is what this is saying. I am only taking the part when x is greater than or equal to 0. So if I'm only looking at half of this, is it a one-to-one function? Yes. So then we could find the inverse. So we change our f of x to a y, switch x and y. If I want to solve for y, normally when you do that, you would add a square root and a plus or minus. If I already know I'm only looking at this positive side, do I have to worry about the negatives? No. So it's just the positive square root. So our inverse is the square root of x. Any questions on that one? So you guys do have about 10 minutes right now, if you want to start some of your homework. So on that last slide, will be due on Tuesday. So Monday, I am not planning to teach anything unless we need to review a little bit after the long weekend.